अच्छा, क्लास सीआर आपके क्लास में तो ऑलमोस्ट फॉरनर्स हैं। अगर हैं तो हम इंग्लिश में फिर लेक्चर स्टार्ट करते हैं। सीआर मौजूद है? क्लास में अभी नहीं है ही नहीं। अच्छा, तो फिर जब आ जाए तो मुझे बता देना कि इंग्लिश में हम फिर शुरू कर लें। अच्छा, लास्ट टाइम हमने अनडैम्प्ड सिंगल डिग्री ऑफ फ्रीडम सिस्टम का रिस्पांस फ्री वाइब्रेशन के दौरान डिस्कस किया था, और उसके लिए हमने एक इक्वेशन भी डिराइव की थी, जो कि ये इक्वेशन हमने डिराइव की थी, जिससे अगर हमारे पास एक सिंगल डिग्री ऑफ फ्रीडम सिस्टम है और उसमें डैम्पिंग नहीं है, यानी कि अनडैम्प्ड सिस्टम है, और फ्री वाइब्रेशन हो रही है, यानी कि वाइब्रेशन हो रही है लेकिन इन द एब्सेंस ऑफ अ फोर्स, तो डिस्प्लेसमेंट और टाइम की वेरिएशन हम इस इक्वेशन से प्लॉट कर सकते हैं। तो एट एनी इंस्टेंट ऑफ टाइम टी हम डिस्प्लेसमेंट की वैल्यू, डायनामिक डिस्प्लेसमेंट की वैल्यू मालूम कर सकते हैं। और इसको अगर आप इस इक्वेशन को ड्रा करें कुछ वैल्यूज लेकर, तो इस किस्म की आपके पास प्लॉट आएगा। अब हम आमतौर पे पीक डायनामिक डिस्प्लेसमेंट में इंटरेस्टेड होते हैं। उसकी वजह मैं आगे एक्सप्लेन करूंगा कि हम पीक डायनामिक डिस्प्लेसमेंट, जिसको यू नॉट से रिप्रेजेंट किया जाता है, उसमें क्यों इंटरेस्टेड होते हैं। तो लिहाजा हमारे पास एक ऐसी इक्वेशन मौजूद होनी चाहिए जिससे हम ये पीक डायनामिक डिस्प्लेसमेंट मालूम कर सके। यहाँ पर एक डिराइव्ड इक्वेशन, डेरिवेशन इसकी बुक में आप देख सकते हैं। डिराइव्ड इक्वेशन में रिप्रोड्यूस कर रहा हूं, जिससे हम अनडैम्प्ड सिस्टम, अगर उसमें फ्री वाइब्रेशन हो, उसमें हम पीक डायनामिक डिस्प्लेसमेंट इस इक्वेशन से मालूम कर सकते हैं। यू नॉट पीक डायनामिक डिस्प्लेसमेंट, u of zero displacement at the start of free vibration, u dot of zero velocity at the start of free vibration, ओमेगा एन नेचुरल सर्कुलर फ्रीक्वेंसी। तो इन वैल्यूज की मदद से हम पीक डायनामिक डिस्प्लेसमेंट मालूम कर सकते हैं। अच्छा, पीक डायनामिक डिस्प्लेसमेंट हम क्यों मालूम करते हैं? एक दफा जब हम पीक डायनामिक डिस्प्लेसमेंट मालूम कर ले, तो उससे हम इक्विवेलेंट स्टैटिक फोर्स की पीक वैल्यू मालूम कर सकते हैं। आप अगर यू नॉट को के से मल्टीप्लाई कर ले तो आपके पास क्या आएगा? के इंटू यू नॉट किसके बराबर होती है? कोई जरा रिप्लाई दे मुझे। फोर्स के बराबर होती है। और यहाँ पर हम से मल्टीप्लाई कर रहे हैं। तो स्टिफनेस जो है इसमें हम इनर्शियल इफेक्ट इग्नोर कर रहे हैं, तो लिहाजा ये जो फोर्स होगी ये स्टैटिक फोर्स होगी या इक्विवेलेंट स्टैटिक फोर्स होगी। तो एक दफा हम अगर पीक डायनामिक डिस्प्लेसमेंट मालूम कर लें, उसको जो भी स्ट्रक्चर आप डिजाइन कर रहे हैं उसकी स्टिफनेस से मल्टीप्लाई कर ले, तो आपके पास पीक वैल्यू ऑफ इक्विवेलेंट स्टैटिक फोर्स आ जाएगी। और यहाँ पर आपका डायनामिक एनालिसिस जो है वो कंप्लीट हो जाता है। इसके बाद आप स्ट्रक्चरल एनालिसिस का कोई मेथड यूज करके एनालिसिस कर सकते हैं और डिजाइन कर सकते हैं। जो रूटीन का मेथड है उसके मुताबिक आप फिर डिजाइन कर सकते हैं। तो डायनामिक डिस्प्लेसमेंट आपका ये U नॉट तक आपका डायनामिक डिस्प्लेसमेंट है। इसके बाद फिर अगेन आपका स्टैटिक एनालिसिस और डिजाइन है वो फिर आप उस पर कर सकते हैं। अच्छा, हमने ओमेगा एन की बात की अभी कुछ देर पहले। नेचुरल सर्कुलर फ्रीक्वेंसी। अब नेचुरल सर्कुलर फ्रीक्वेंसी जिसका यूनिट रेडियन पर सेकेंड है, इसकी फिजिकल इंटरप्रिटेशन जो है बिगिनर्स के लिए समझना मुश्किल होता है। इसके बजाय अगर हम साइक्लिक फ्रीक्वेंसी जो है मालूम करते हैं तो उसको विजुअलाइज करना निस्बतन आसान होता है। और साइक्लिक फ्रीक्वेंसी एफ या नेचुरल सर्कुलर फ्रीक्वेंसी से रिलेटेड जो साइक्लिक फ्रीक्वेंसी है यानी कि नेचुरल साइक्लिक फ्रीक्वेंसी एफ एन, तो ये आपको पता है कि एफ एन और ओमेगा एन के दरमियान ये रिलेशन एग्जिस्ट करता है। तो ओमेगा एन अगर आप मालूम कर ले तो आप एफ एन मालूम कर सकते हैं। और एफ एन का जो यूनिट है वो साइकिल पर सेकेंड या हार्ट्स है। और इसकी डिफिनीशन ये है कि सिंगल डिग्री ऑफ फ्रीडम सिस्टम में अगर फ्री वाइब्रेशन हो रही हो तो वन साइकिल ऑफ वाइब्रेशन कंप्लीट होने में जितना टाइम लगेगा, नहीं सॉरी, 1 सेकेंड में जितने वाइब्रेशन साइकिल्स कंप्लीट करेगा वो उसकी नेचुरल साइक्लिक फ्रीक्वेंसी हो। नेचुरल साइक्लिक फ्रीक्वेंसी से भी फिर निस्बतन ज्यादा कन्वीनियंट जो टर्म है वो है नेचुरल टाइम पीरियड या नेचुरल पीरियड ऑफ फ्री वाइब्रेशन। दोनों एक ही चीज है, TN, और इसका यूनिट जो है सेकंड है। और ये जो है इट इज सिंपली द रेसिप्रोकल ऑफ नेचुरल साइक्लिक फ्रीक्वेंसी। इसको विजुअलाइज करना फिर काफी सिंपल है। इसकी डिफिनीशन जो है वो ये है कि नेचुरल टाइम पीरियड ऑफ सिंगल डिग्री ऑफ फ्रीडम सिस्टम इज द टाइम required by the system to complete one cycle of vibration during free vibration. और अगर आपके पास डायनामिक डिस्प्लेसमेंट से डिस्प्लेसमेंट टाइम वेरिएशन आ गई है तो आप उससे ये नेचुरल टाइम पीरियड आप इजीली मालूम कर सकते हैं। फार्मूले से भी मालूम कर सकते हैं, ग्राफ से भी आप मालूम कर सकते हैं। इसको मजीद मैं एक्सप्लेन अगर करता हूं तो ये एक सिंगल स्टोरी फ्रेम नीचे ये कर्सर की मूवमेंट के साथ आप देखें, ये इसकी पोजीशन जी। अच्छा अच्छा। Okay, so let's consider the uh, uh, various position of a single story frame. Say its position under static equilibrium is A, and as you can see from this graph that since it is static equilibrium position, so displacement are zero and the structure is undeformed. Now due to if the structure is experiencing free vibration and it displays in the rightward direction, and the peak dynamic displacement is u naught. And when the structure deformed by peak dynamic displacement, its position is represented by B. On this graph, B is this point. Now, since the structure is vibrating, system is undamped, after displacing to the right, it will come back to its original position C, and then it will deform in the opposite direction by the same amount u naught, and then it will come to its original position. This is one cycle of vibration, and the time required in one cycle of vibration is known as natural time period, or the time required from A to E, which is one cycle, is known as natural time period. This is, as you can see, the natural time period is quite easy to visualize. Any question? Okay. So if there is any question, I will provide natural time period of some structures. The first one is Alcoa building in San Francisco, which is made of steel structures, 26-story height. Its natural time period in various directions are determined with the help of instruments installed in the building, and it is determined that natural time period in east-west direction is 2.21 seconds. In other words, when this building is vibrating, the time required to complete one cycle of vibration is 2.21 seconds. And the time required to complete one cycle of vibration in north-south direction is 1.67 seconds. And the time required when the building is twisting, the time required to complete one cycle of vibration is 1.12 seconds. All these values are based on experimental data. For that purpose, instruments were installed in the building and the vibration record was recorded. From that vibration record, these values were determined. Now another structure, Golden Gate Bridge, San Francisco, which is made of steel, and a central span of the bridge is 4,200 feet. Again, the natural time period in various directions were experimentally determined, and the natural time period is transverse direction. This direction is 18.27 seconds because the system is quite long, so it is very flexible and it will take a lot of time to complete one cycle of vibration. The period of vibration in vertical direction is 10.9 seconds. In longitudinal direction, it is 3.81 seconds, and the torsional time period is 4.43 seconds. For building structures, there is a thumb rule with the help of which you can estimate the natural time period, but this rule is quite accurate up to 12 stories. But if the building height exceeds 12 stories, then this formula is not accurate, but still it gives you some idea. According to this thumb rule, the natural time period of a building structure can be calculated by dividing the number of stories with 10. So if you have a 7-story building, according to this equation, the natural time period will be 7 divided by 10, 0.7 seconds. So if there is any question, I will wait for 10 seconds. If there is any question, you can ask, otherwise I will proceed.
No, sir.
Okay, so a beam which is shown in figure is pulled for 1/4 inch in the downward direction and then suddenly released to vibrate freely. We have to calculate the natural time period of the system and solve the equation of motion to determine the amplitude of equivalent static force. So natural time period can be determined if we have the stiffness and mass. Mass can be calculated from the lumped weight, and stiffness of cantilever beam is 3EI over LQ. And we will ignore the self-weight of beam as the lace damping effect. The problem is quite simple. This is equation of motion for undamped system. K for cantilever beam is 3EI over LQ. We have the value of E, I, and L, and the calculated value of K is 7.55 kip per inch. Since we have to be consistent, so since we will use the value of mass in slugs, pound second per square feet, so therefore we shall convert this value into pound per feet, and 7.55 kip per inch equal to 90625 pound per foot. Now the value of mass. Once we find these values, we can find natural circular frequency, and then we can calculate natural time period by this equation, which in this case is 0.114 seconds. So we have calculated natural time period. The second part is to determine the peak value of equivalent static force. For that purpose, we need to find the peak value of dynamic displacement. And the peak dynamic displacement can be determined. Peak dynamic displacement can be determined by the equation which was discussed few slides ago. This equation, in this case, displacement at the start, u of 0 is the displacement at the start of free vibration. U dot of 0 is velocity at the start of free vibration. Since the cantilever beam was displaced by 1/4 inch, and after that free vibration started. So therefore displacement at the start of free vibration was 1/4 inch or 48 feet. And the velocity was 0. So if we substitute these values, the peak dynamic displacement comes out to be 1/48 feet. And the peak value of equivalent static force, which can be simply determined by multiplying u naught with k, comes out to be 1888 pounds. So the summary is that for given conditions, this beam need to be designed for a force of 1000 pound weight plus 1888. So we have to design this system for a total weight of total load of 288 pounds. ये इसकी समरी होगी. Now problem 4.2. In this case, we will solve equation of motion for the frame shown in problem 3.3. In problem 3.3, we developed the equation of motion for this system. Now we will solve the equation of motion, and if the displacement and velocity which occur in the same direction at the start of free vibration are 0.003 feet and 0.2 feet per second, we will determine amplitude of dynamic displacement, that is peak value of dynamic displacement, and the corresponding equivalent static force Fs naught. So as far as solving the equation of motion is concerned, we discussed the solution to equation of motion for undamped system subjected to free vibration. पीछे आपने this is the solution. So u of 0 is given, u dot of 0 is given, omega n can be determined with the help of stiffness and mass, which is 34.79 radian per second in this case. We have all the values. So you just need to substitute these values in equation and you get this solution, which can be experimentally plotted, which can be plotted graphically if we substitute different values of t. आप t की different values ले लें, डायनामिक डिस्प्लेसमेंट की मुख्तलिफ वैल्यूज आएंगी, इसको आप ग्राफिकली प्लॉट कर सकते हैं. And you can also find the peak value of dynamic displacement from the graph. A is by this equation which gives you a peak dynamic displacement of 0.0065 feet. Now at this stage the dynamic analysis is over and now we can analyze the structure by routine methods of structural analysis and then we can design the structure for specific material. So you just need to multiply this with stiffness to find the peak value of equivalent static force, which in this case is 24.38 kg. If I summarize this problem, this is actual structural system which is experiencing free vibration and displacement at the start of free vibration was 0.003 feet. Velocity at the start of free vibration was 0.2 feet per second. The equivalent effect of these values is a static force of 24.4 kg in the lateral direction. ये जो peak displacement और velocity की at the start of free vibration अगर ये values हों तो अगर आप इसको एक static force के लिए डिजाइन करना चाहेंगे तो उस केस में आप जो कैलकुलेशन से भी हमने मालूम की है 24.4 के स्टैटिक फोर्स ले लें और इसके लिए आप एनालाइज करके डिजाइन कर सकते हैं. Any question? Okay, this is exercise for your practice. Answer are given. Only 16 students are here. So with this, the response of undamped system subjected to free vibration is completed. And now we will start a response of damped system when subjected to free vibration. And since we are considering dash part systems for damping, so strictly speaking, we will deal with the response of viscously damped system when subjected to free vibration. So again, we will develop an equation to we'll solve the equation of motion for viscously damped system under free vibration. So in this case, the term P of t will be zero because no external force. Again, the solution to this second order differential equation, one of the possible solution to the above second order differential equation is this. If we differentiate it once and twice, we will get the value of u dot and u double dot. Simply insert those values in this equation. And which can be rewritten in this form. Again, the product of these two terms is zero. Since the term written in the right, on the right side in parentheses cannot be zero, the only possibility is that this term can be zero. So if we take this zero and solve this quadratic equation, it will have two roots. S will have two roots. This equation can be simplified and rewritten in this form. Now we have the relation omega n is equal to under root k over m. K is equal to m omega n square. So if we use this value of k in this equation, we will get the equation will convert to this form. Now if we rearrange this equation, that is we multiply and divide with omega n. अगर हम यहाँ पर जो ये इसको ओमेगा एन से मल्टीप्लाई डिवाइड कर लें, हमारे पास ये फॉर्म आ जाएगी. नाउ दिस c by 2m omega n this c by 2m omega n is known as zeta. No, sorry. This 2m omega n is represented by C subscript CR, critical damping coefficient. 2m omega n को critical damping coefficient कहा जाता है. this C by 2m omega n, which can be written as now C by C subscript CR, is known as damping ratio. And this is represented by zeta. Now, based on the value of zeta, there are three possibilities. Either zeta is less than 1, or equal to 1, or greater than 1. लेकिन जीटा की 3 पॉसिबिलिटीज हो सकती है. ये रेशो जीटा 1 से कम होगी, या 1 के बराबर होगी, या 1 से ज्यादा होगी. Based on these 3 possibilities, we can classify a damped system in 3 types. But before discussing that, I will once again come to the original, we will come to the definition that C by 2m omega n is C sub is known as zeta, and if in previous equation इसमें अगर हम ये C by 2m omega n को अगर हम zeta से replace कर लें, we will get this equation. Omega n into under root 1 minus zeta square is known as damped natural frequency, and it is represented by omega d. Now, as I said, that there are 3 possibilities. The damping coefficient C, if either it is greater than C subscript CR, or the first possibility is that C is equal to C subscript CR, or C by subscript CR, which is damping coefficient, is equal to 1. Such systems are known as critically damped systems. The second type of systems are those in which C is greater than C subscript CR. ये 2m omega n जो है क्या चीज है? C subscript CR. So if C is greater than critical damping coefficient, or in the other word, damping ratio exceeds 1, such systems are known as overdamped systems. And if the value of C is less than critical damping coefficient, or in the other words, damping ratio is less than 1, then such systems are known as underdamped systems. So we will discuss now one by one all these 3 systems. First of all, critically damped system, in which C is equal to 2m omega n, or C is equal to critical damping coefficient, or in the other words, damping ratio is 1. In this structure, in this type of systems, there is no vibration. Definition of vibration is to and fro motion. In this case, if you disturb the equilibrium position, the system will come back to its original position without displacing in the opposite direction. So there will be no to and fro no to and fro movement, so there will be no vibration. However, the system or structure return to its original position in shortest possible time. Examples of critically damped systems are recoil mechanisms. For examples, rockets, launching rockets, missiles, guns, etc. In this case, for example, if someone is using a gun, a soldier is using a gun, if he fires, the gun spring within the gun shall come back to its original position in minimum amount of time. Otherwise, it will take a lot of time to have a second fire. Similarly, if the spring system in a gun is such that it experiences vibration, then of course the accuracy will be compromised due to vibration. The accuracy of fire will be compromised. Therefore, such type of systems are designed as critically damped systems. Now, over damped system. If C is greater than critical damping coefficient or damping ratio is greater than 1, systems are overdamped. However, like critically damped system, there will be no vibration. However, the system will come back to its original position in relatively much time as compared to the critically damped system. In critically damped system, the system will come back to its original position in shortest possible time, but in overdamped system, it will take relatively more time depending upon the damping ratio. Greater the value of damping ratio, greater will be the time taken to come back to its original position. Examples of overdamped system. One of the example of overdamped system is this automatic door. In this case, if you open this door, you have sufficient time to enter the room. If we design it as a critically damped system, what will happen? You open the door, you want to enter the room, but it will come back to its original position in very less time, and it will hit you. It will collide with you. So automatic door systems are designed as overdamped system. The third type of system is underdamped system, in which viscous damping coefficient C is less than critical damping coefficient, or damping ratio is less than 1. In this case, now the vibrations occur. In first two cases, critically damped, overdamped system, no vibration occurred. In this case, the vibration occur, and the system take a lot of time to stop, and most of our civil engineering structures I will say all of the civil engineering structures have a damping ratio less than 1. So from civil engineering or structural engineering point of view, this is more important to us. Structural system occasionally have a damping ratio greater than 0.05 or 5%. Mechanical systems can be critically damped, over-damped systems. So critically damped, over-damped systems are more important for mechanical engineers, but not important for civil engineers. For civil engineers, the only important type of system is under-damped system, and therefore we will focus on under-damped systems. Now here, with the help of an example, you can see various types of damped systems. Okay, here you can see that this ruler is attached to cork with the help of some pin. At the free end of this ruler, a magnet is suspended. Here a magnet is suspended, and there is an aluminium block. Now this aluminium block exert magnetic force. Initially, you can see the distance between the aluminium block and the magnet. From this point to this point, this is distance. And the equilibrium position is disturbed. Now you can see the system is vibrating, but due to magnetic force in each cycle of vibration, this will be but due to magnetic force, damping will occur in each cycle of vibration. The amplitude of displacement will reduce, you can see. Now, the distance between the aluminium block and the magnet is reduced. Consequently, magnetic forces will increase. Damping force will also increase. And now the amplitude of displacement will quickly reduce in each cycle of time, and eventually the system will come back to its original position. You see in each cycle, peak displacement is reducing. अच्छा, जरा आप बताएं ये कौन सा सिस्टम है, क्रिटिकली डैम्प्ड सिस्टम है, ओवर डैम्प्ड सिस्टम है, अंडर डैम्प्ड सिस्टम है?
अंडर डैम्ड है मेरे ख्याल में सर।
हाँ, अंडर डैम्ड किस वजह से? बिकॉज देयर आर वाइब्रेशंस. ओवर डैम्प्ड सिस्टम एंड और क्रिटिकली डैम्प्ड सिस्टम में वाइब्रेशंस नहीं होती. यहाँ पर वाइब्रेशन हो रही है, तो दिस इज क्रिटिकली डैम्प्ड सिस्टम. Now the distance between aluminum block and the magnet is further reduced, and now you can see Due to higher magnetic forces, energy was dissipated in relatively less amount of time, but since to and fro motion occurred, still it occurred, so it is still an underdamped system. However, the damping ratio is increased now. Further reduction, vibrations are still occurring, so system is critically underdamped. Vibration are still occurring, still it is underdamped, but the damping ratio is increasing. Still vibrations. Still one cycle of vibration occurred. Now it come back to its original position, लेकिन ये अपनी ओरिजिनल पोजीशन के आने के बाद लेफ्ट साइड पे ये नहीं किया है, वाइब्रेशन नहीं हुई है. So now it is not an underdamped system. And there are two possibilities. Either this is critically damped system or overdamped system. You can find yourself after watching the remaining part of this video. Now the time required to come back to its original position is increasing. So the first one was critically damped system, the rest are overdamped systems. So okay, we will have a 20-minute break, and then exact at 9:20 we will start our class, and at 10 a.m. there will be a quiz. ठीक है, आप जाना चाहें जाएं, 20 मिनट के बाद आ जाएं.